JMB, how are you all? I hope you all are good. I welcome you all to my YouTube channel. My name is Prince Ranpara. I am a PhD scholar in the Department of Chemical Engineering at the Indian Institute of Technology, DOPA. So in today's lecture, we are going to solve one numerical example based on the plug flow reactor. So let's get started. So main aim of this today's lecture is to analyze and estimate how large volume of reactor is required in order to achieve the desired conversion of the reactants and the formation of desired product by using the plug flow reactor. Okay, so we are in today's lecture we are going to solve one industrial example by using the plug flow reactor, right? So before beginning of this today's lecture, we need to have a detailed understanding of the fundamental concept of the plug flow reactor, which I have explained you in a very simplified way in the previous lecture, lecture number 8. Okay, if you want to recall, I request you to please watch the previous lecture, lecture number 8. So let's get started. Okay, the main aim of the today's lecture is to understand and analyze and estimate how large volume of plug flow reactor is required in order to achieve the desired conversion of reactants and the formation of the desired product by using the plug flow reactor. Okay, so we are going to solve an industrial example of the plug flow reactor. Okay, so here you can see the example, right? So the question stated here: let's consider the liquid phase cis-trans isomerization of 2-butene, where cis-2-butene is converted into trans-2-butene by using the plug flow reactor, okay, which we will write symbolic as A gives B. Okay, the reaction is first order in AA. The rate law is given as minus RA is equal to KCA and is carried out in a tubular reactor in which the volumetric flow rate is nu is constant, that is nu is equivalent to nu naught. Okay, and the diagram is being displayed. Okay, so first of all we understand the question, right? So by using the plug flow reactor, we are carrying out cis-trans isomerization reaction where cis-2-butene is symbolized as A, which is reactant. Cis-2-butene is converted into trans-2-butene, which is product, which is symbolized as B, right? So reaction is carried out in a plug flow reactor or tubular reactor, right? So where the reactants A are getting transformed into the new products B. Okay, so they have also mentioned we are carrying the reaction in the liquid phase, which means by using the plug flow reactor we are carrying the first order reaction with the given rate law minus RA is equal to KCA liquid phase. Okay, so we are carrying the first order liquid phase irreversible reaction by using the plug flow reactor. Okay, where the volumetric flow rates are constant, which means the exit volumetric flow rate is denoted by nu, and the inlet volumetric flow rate, which is entering to the plug flow reactor via inlet stream, is indicated by nu naught, right? Okay, so first of all we'll understand the diagram, right? So here this diagram represent the plug flow reactor. Okay, so here via inlet stream, okay, where the inlet volumetric flow rate is nu naught, where the reactants are fed into the reactor via inlet stream into the reaction environment of the plug flow reactor. The initial concentration of the reactants is denoted as Ca naught, right? Concentration of A, initial concentration of A, okay, is denoted as Ca naught. In the reaction environment, the reactants will get converted into the new product. Reaction will take place in the reaction environment and reactants will get converted into the new product with respect to the progress of the time, okay, and with respect to the volume of the plug flow reactor in the axial direction, right? After completion of the reaction, the product will exit through the outlet stream with the unreacted reactants, right? The product with unreacted reactants will exit through the outlet stream of the plug flow reactor with the volumetric flow rate nu. Okay, I hope up to here it is clear. So here they have mentioned in the question A that the volumetric flow rates are constant, which means the exit volumetric flow rate from the plug flow reactor is equivalent to the inlet volumetric flow rate which is entering into the plug flow reactor, which means the nu is equivalent to nu naught, right? volumetric flow rate, which means the volume of the fluid which is entering with respect to the time in the plug flow reactor, right? The volumetric flow rate, which means the volume of the fluid which is entering into the plug flow reactor with respect to the time. Okay, it's called the volumetric flow rates, right? I hope up to here it is clear. Okay, now we'll solve the first part of the question, right? So I request please read the first part of the question. The first part of the question, which is stated as, without solving any equation, sketch what you think the concentration profile Ca as a function of volume would look like, right? So we need to sketch, we need to plot a graph between the concentration as a function of volume, right? So the question which says, we need to understand how the concentration varies with respect to the volume and length of the plug flow reactor in the axial direction, right? So how the concentration changes with respect to the volume and the axial direction in the plug flow reactor. Okay, so let's get started. So here is the first part solution of the, here is the first part solution. Okay, so we'll solve. So let's say, so here we'll use the fundamental concept and understanding of the plug flow reactor, right? So let's say the inlet stream, the inlet stream is the reactants are feeding to the plug flow reactor via inlet stream, right? Where the volumetric flow rate is mu naught. Initial concentration is Ca naught, right? So at the initial volume of the, so let's say at the initial volume of the plug flow reactor, where we'll have the higher concentration of the reactant presence in the reaction environment, right? So due to the first order reaction, where the rate of the reaction is equivalent, is directly proportional to the concentration of reactants, right? Okay, so at the initial volume of the plug flow reactor, where we are having higher concentration of reactants present in the reaction environment of the plug flow reactor, right? So due to the higher concentration of reactants present in the reaction environment in the plug flow reactor, we'll have the higher rates of the reaction, which means with the higher rates of the reaction, the more amount of concentration or more amount of molecules of reactant molecules will get converted into the new product, right? So the rates will be very high, the reaction will take place very high because of the presence of higher concentration. If you are having higher concentration presence, the rate of the reaction will be very high according to the first law, according to the first order reaction, right? Okay, so for those reasons, if we plot the graph between concentration versus volume, we can see that at the initial volume of the plug flow reactor, where we are having the steepest slope, right? Steepest slope. Okay, here you can see we have the steepest slope, right? Due to which means with respect to the volume of the plug flow reactor, the concentration, due to the higher concentration present in the plug flow reactor, we are having the higher rates of the reaction, due to which more amount of with the higher rates of the reactants, more reactants will get consumed, will get disappear from the reaction environment, and will get converted into the new products B with the higher rates, due to which we have a very steep slope, and the nature of the curve is decaying in the exponential, right? The concentration decays in exponential, right? Okay, I hope up to here it is clear. Now let's say up to this part where let's say up to this part where we have the steepness of the slope decreases, which means let's say from here volume, from here to here volume, this much volume, where we have lower concentration of reactants present in the reaction environment. Okay, due to the lowering of the concentration in the reaction environment, the rates of the reaction will also decrease, due to which the formation of the new product will also decrease, and the conversion of the reactants into the product will also decrease. Due to those reasons, the steepness of the slope will also decrease. Okay, I hope the nature of the curve you have understood. Okay, in this part. Okay, in the end in this part, let's say at the outlet stream of the plug flow reactor, where the product in reactants will exit through the outlet stream of the plug flow reactor, where you can see the product which is formed in the reaction environment of the plug flow reactor will exit with the outlet stream of the plug flow reactor. Okay, and unreacted reactants, the reactants which does not take part in the reaction, are called the unreacted reactants, right? So with the product unreacted reactants will also exit through the outlet stream. Okay, I hope up to here it is clear. Okay, so you can see the nature of the curve. Okay, so here we have to plot, we have to sketch, okay, and we have to plot a curve between concentration as a function of volume, right? So the initial volume of the plug flow reactor, where we are having the higher concentration of reactants presence, right? So here we have the highest concentration of reactant presence, right? So we'll start from here and slowly and gradually, with respect to the progress of the time, with respect to the progress of the reaction, the concentration of the reactant will get decreased. Okay, so due to those reasons, we have the exponentially decay in the concentration of reactants. Okay, I hope it is clear. Okay, so here we have completed the first part solution. Okay, so you need to draw this graph. Okay, and you need to also explain how. So let's say the molar flow rates of A and concentration of A both get decreased. Okay, the volumetric flow rate is constant, which means here we are carrying out first order liquid phase irreversible reaction in the plug flow reactor, which means volumetric flow rates are constant, which means in the liquid phase the density will remain constant. Okay, density of the fluid will not change with respect to the progress of the reactions, right? So density of the fluid stream will remain constant, due to which the volumetric flow rates will also remain constant. Okay, I hope you have understood. Okay, so let's say if we want to understand what the concentration means, so concentration is the ratio of molar flow rates with respect to the volumetric flow rates. Okay, I hope you understood the first part. Now we'll solve. So here we have completed the solution of the first part. Now we'll solve the second part, right? So I request you to please read the second part. The second part of the question, which stated has, derive an equation relating the reactor volume to the entering and exiting concentration of A, the rate constant K, and volumetric flow rate nu naught. Okay, so in the second part of the question, where we have to derive an equation which relates volume to the other operating parameters, right? So in the second part of the question, we need to derive an equation which relates volume as a function of volumetric flow rate nu naught, rate constant K, exiting exiting concentration Ca, and entering concentration Ca naught, right? So here we need to derive an equation which relates the volume, and volume is a function of volumetric flow rate nu naught, rate constant K, entering concentration Ca naught, and exiting concentration Ca, right? So in order to solve the numerical, we'll always start with the mole balance, right? So first step is to write the mole balance, second step is to write the rate loss, third step is to combine both the mole balance with the rate loss and to make some rearrangement in the equations, and we need to derive. Okay, and the fourth step is to solve by applying the integral. Okay, and fifth step to make some rearrangement and to derive with the final equation, right? So let's get started. So we are solving the second part of the question, right? So first step is to write the mole balance. So mole balance is denoted as Ra is equal to dFA by dV, right? So we are using the plug flow reactor, then we'll write the mole balance of plug flow reactor, right? So Ra is equal to dFA by dV, which means how the molar flow rates, how the moles of reactants will change with respect to the volume of the reactor. It's okay. And second step is to write the rate law. The rate law, as per the given information in the question, we are carrying out the first order reaction, liquid phase reaction, and irreversible reaction, right? So first order reaction is the first order reaction which has the rate law of minus Ra is equal to Kca, which means here we can see the rate of the reaction is indirectly proportional with the concentration of reactants. Okay, so which means if we are having the higher concentration of reactants present in the reaction environment of the plug flow reactor, we will have the higher rates of the reaction. As the concentration with respect to the progress of the time, with respect to the progress of the reaction, as the concentration of reactant decreases, the rate will also decrease, due to which the conversion will increase, rate of the reactant rate of the reaction will decrease, right? With respect to the volume of the plug flow reactor, in the axial directions. Okay, now here we already know the volumetric flow rate is constant. For those reasons, nu is equivalent to nu naught. Okay, volumetric flow rates are indicated by nu. Okay, the exiting volumetric flow rate is nu and the entering volumetric flow rate is nu naught. Volumetric flow rate, which means the volume of the fluid which is entering into the plug flow reactor with respect to the time, is called the volumetric flow rate. Okay, the volumetric flow rate can also be defined as the ratio of molar flow rates with respect to the concentration. Okay, volumetric flow rates can be also defined as the ratio. If we are writing in terms of concentration, if we are writing volumetric flow rates in terms of reactants, right, then volumetric flow rates of reactants is equivalent to molar flow rate of reactant A and concentration of reactant A, right? So for both the case, exit volumetric flow rate and entering volumetric flow rate, we can write likewise, right? So exit inlet volumetric flow rate, the volumetric flow rate, which means the volume of fluid which is entering into the plug flow reactor, is denoted by nu naught, is equivalent to the molar flow rate, initial molar flow rate, okay, divided by initial concentration of reactants which are entering into the plug flow reactor. Okay, now let's say if we make the subject as molar flow rates, right, Fa, if we make the subject as Fa, then we can get the equation as Fa is equivalent to Ca into nu, right? So let's say if we are making the subject as Fa is equivalent to Ca into nu, same way for the initial molar flow rates is equivalent to the product of initial concentration with the initial volumetric flow rate. I hope up to here it is clear. Okay, now we'll solve the second part of the question. Okay, so first of all we need to write the mole balance equation. So we are writing Ra is equal to dFA by dV, right? Ra is equal to dFA by dV. Okay, now let's say we need to derive a relation which relates volume with volumetric flow rate nu naught, rate constant K, initial concentration Ca naught, and final concentration Ca, right? So let's say by using the mole balance equation, where here you can see the Ra consists of Kca, right? So we already have rate constant and final concentration of reactants. Okay, so from dV we can get volume V, right? So we have volume. Now the remaining variables are V naught and Ca naught, right? So we can substitute Fa by its value. Okay, we can substitute Fa by its value. So from here we can get Ca and volumetric flow rate nu. Okay, so let's say we are substituting the value. So Ra is equal to d of Ca nu by dV. Okay, now let's say here the volumetric flow rates are constant, so the initial final volumetric flow rates are equivalent to the initial volumetric flow rate, right? So due to those reasons we can replace the nu to nu naught. Okay, while remaining other term has same, so dCA of nu naught by dV. Now the volumetric flow rate is constant, due to which we can take out the volumetric flow rate out of the differentiation, right? So we are taking the V naught nu naught from the differentiation, so we are getting nu naught into dCA by dV, right? So from here we can get the mole balance of plug flow reactor as Ra is equal to nu naught dCA by dV. I hope up to here it is clear, right? Now let's say now we'll combine the equation 4. Now the third step is to combine the mole balance with the rate law. So we are combining the mole balance with the rate law. Okay, so in this third step we are combining equation 4 and equation 3, and we get, let's say we are writing minus Ra is equal to Kca rate law. So we are putting the value of Ra which we have obtained here, right? So minus Ra, we are putting the value from here, V naught dCA by dV is equivalent to Kca, right? Now here we are aiming to make the equation which relates volume, right? Volume as a function of nu naught K, Ca naught C, right? So for those reasons we are making the subject as dV. So we are making the subject as dV, and we are taking this Kca into the denominator. Okay, so we are making the subject as dV is equal to minus V naught by K dCA by Ca. Okay, so here we have obtained the differential form of the equation, right? Okay, so this equation phi represent the small, infinitely small differential element of the infinitely small differential element of the volume of the plug flow reactor, right? But we need to account for the entire volume of the reactor. Okay, this equation phi represent a very small, infinitely volume element of the plug flow reactor, but we need to account for the entire volume of the plug flow reactor, right? So due to those reasons, we'll apply the integration sign, right? So by applying the integration sign, we can sum up all those infinitely small differential element of the volume of the plug flow reactor, right? So by applying the integral sign, it will make the calculation simple, right? So let's say we are applying integration on the both sides of the equations, right? So integral dv from limits 0 to v. So how these limits came? So let's say the initial volume of plug flow reactor is from v is equal to 0 to v is equal to v, right? So here v1 we are writing as v. Okay, so integral 0 to v dv is equivalent to minus v naught by k integration of ca naught to ca dca by ca, right? From initial concentration of reactant ca naught to the final concentration ca, integration of dca by ca. Okay, now after following the integrations, where we'll apply integration of dv is v, and we'll apply the limits from v minus 0. So we will remain only v on the left hand side is equal to minus v naught by k, and integration of dca by ca is ln ca. Okay, limits from ca naught to ca. Okay, integration of dx by x is ln x, right? So we are using same formula, so ln ca from limits ca naught to ca. Okay, so after further solving, where this term will remain as it is, minus v naught by k, and we are applying the limits. Okay, so ln ca minus ln ca naught. Okay, ln ca minus ln ca naught. Now again we are using the mathematical relation, right? So minus v naught by k will remain as it is, and ln ca minus ln ca naught can be written as ln ca by ca naught. Okay, for example, ln x minus ln y can be written as ln x by y. Okay, same relation we are using here. So we obtain the final form, right? So we can compare the v is equivalent to minus v naught by k ln ca by ca naught. Okay, so in order to make this negative sign to positive, so what we can do, we can just do reciprocal. Oh, okay, so here the denominator ca naught will go into the numerator, and the numerator ca will come into the denominator. By doing this reciprocally of the ca naught into the numerator and ca into the denominator, the negative sign can be cancelled off. Okay, so finally we are getting v is equivalent to v naught by k ln ca naught by ca. Okay, so finally we have derived a relation where the volume v is equivalent to v naught by k ln ca naught by ca. Okay, so here we have derived a relation which relates volume with the initial volumetric flow rate nu naught, with the rate constant k, with the initial concentration ca naught, and the final concentration ca. Okay, so here we have completed the solution of the second part of the question, right? I hope up to here you have understood. Now let's solve the third part of the question, right? So I request you to please read the question. Okay, the third part of the question, which stated has, determine the reactor volume V1 necessary to reduce exiting concentration to 10% of entering concentration, that is Ca is equivalent to 0.1 Ca naught, when the volumetric flow rate is nu naught is 10 cubic decimeter per minute, which means 10 liters per minute. Okay, and the specific reaction rate K is 0.23 minute inverse. Okay, so in the third part of the question, we need to calculate the volume V1 which is required. We need to calculate the volume V1 which is required in order to achieve the desired conversion of 90%, right? So by using the plug flow reactor, we are aiming to achieve the desired conversion of 90%, right? Okay, So how large volume of plug flow reactor is required in order to achieve the desired volume of 90, desired volume and the desired conversion of 90%, right? So we are solving the third part. Let's say we need to find the volume V1 at which the exiting concentration is 10% of initial concentration, right? The exiting concentration is 10% of initial concentration. Okay, so let's say, for example, let's say in the plug flow reactor via inlet via feed stream, the 100 reactant molecules are entering in the plug flow reactor, right? So for example, let's consider 100 molecules is equivalent to 100%. Okay, so let's say 100 molecules are feeding to the reaction environment of the plug flow reactor via inlet stream. Okay, so in the reaction environment, the 100 molecules will react and get converted into the new product. Okay, after completion of the reactant with the volume V1, after completion of the reaction, the 90 total 90 molecules out of 100 molecules, so total 90 molecules have converted into the new products, right? And only 10 molecules are remaining unreacted. Okay, so those unreacted 10 reactant molecules will exit via outlet stream with the products. Okay, it's called the CA. Okay, so CA is the exit concentration of reactants is equivalent to the 10% of initial concentration. Okay, so we can write CA is equivalent to 0.1 CA naught. Okay, so in order to achieve the desired conversion of 90%, in order to achieve the desired conversion of 90%, how large the volume of reactor plug flow reactor is required? Okay, so we need to calculate V1. Okay, I hope you have understood. So in the question we have we have provided the values of rate constant is equivalent to 0.23 minute inverse. The volumetric flow rate nu naught is equivalent to 10 cubic decimeter per minute, which is equivalent to 10 liters per minute. Okay, so now in order to calculate the volume V1, we can use the equation 7, right? So by using the equation 7, we can calculate the volume V1 required to achieve the 90% conversion of the reactants in the reaction environment of the plug flow reactor, right? So we are writing V1 is equivalent to V naught by K, nu naught by K, ln Ca naught by Ca. Okay, so we have the values of volumetric flow rate, just plugging all the values. Okay, so V1 is equivalent to V naught value we have 10 cubic decimeter per minute, rate constant value is 0.23 minute inverse, ln Ca naught will remain as it is, and Ca we can keep as Ca is equal to 0.1 Ca naught, right? 0.1 Ca naught. So from here, numerator and denominator, the Ca naught can be cancelled off. Okay, so after solving this term, we'll get the answer is 43.4783 cubic decimeter, and ln of 1 by 0.1 is ln of 10. Okay, after solving that, ln of 10 is 2.3026, right? And we are multiplying with this term, so finally we'll obtain the volume of V1 is equivalent to 100.1131 cubic decimeter, which is equivalent to 100 liters. Okay, 100 liters, which means in order to achieve 90% conversion, we required 100 liters of volume, right? In order to achieve, so these represent 90% conversion, right? 90% conversion, right? In order to achieve 90% conversion, we required 100 liter. Okay, 100 liter volume of plug flow reactor. I hope you understood. Okay, so here we have completed the third part solution. Okay, I hope you have understood. Now let's say we are okay, so here we have completed the entire solution of the question 1. Okay, now we are solving something extra, right? Now let's say, what if, now the question which arises in our mind, okay, now what if I want to achieve the desired conversion of reactants to be 99%, right? Then how large the plug flow reactor is required, right? How large volume of plug flow reactor is required in order to achieve 99% conversion of the reactants and the formation of the desired product, right? Okay, so let's say we'll calculate how large volume of plug flow reactor is required in order to achieve 99% conversion, okay, by using the plug flow reactor, right? So let's say we are now calculating V2, okay, in order to achieve 99% conversion, right? So this represents 99% conversion, okay. So conversion is denoted by X, okay. So conversion which means the reactants are getting converted into the product is called the conversion, okay. So we'll understand what the term means conversion in the next chapter, upcoming chapter number 2, okay. So let's say the conversion have the two ranges. The conversion can range from 0 to 1, and the conversion can also range from 0% to 100%, okay. So let's consider the outlet stream, where the concentration of the outlet stream of reactants is 99 is 1% of the initial concentration, right? 1 by 100 path, which means the outlet stream consists even very trace amount of unreacted reactant, right? Very trace amount. For example, let's consider first example, right, where we have 100 molecules which feed into the reactor, Plug Flow Reactor. After the completion of the reaction at volume V1, which is now 100 liters, right? After 100 liters of volume, now the product is exiting with the unreacted reactants, right, through the outlet stream, right? So here we had a 10 unreacted reactants remained, right? Now let's say, now if we want that 10 reactant molecules we want to convert into the product, right? Then how large reactor volume Plug Flow Reactor will be required in order to convert those 10 reactant molecules, right? Or for example, those 10% of unreacted reactants, okay, we need to convert all those 10% unreacted reactants into the product. Then how large volume of Plug Flow Reactor is required, right? So we are calculating that, okay. So let's say, for example, if we are aiming for 99% conversion, which means out of those 10 molecules, we are aiming for 9 reactant molecules to convert into the new products, right? And remaining with the only 1% of the unreacted reactant, right? 1% of the unreacted reactant is 1 by 100, right? So here we can, so 1 by 100 of initial concentration Ca0, which is 100 molecules, right? So we can write the outlet concentration of reactant has Ca is equivalent to 1% of initial concentration Ca0, okay, 0.01 of Ca0, right? So let's say conversion is 1 minus 0.01 is equivalent to 99. So if we do 0.99 into 100, which means 99% conversion. If we want to achieve 99% conversion, then how large volume of reactor is required, okay? So we are calculating. So again, by using the same formula, we can use to calculate the volume, right? So V2 is equal to nu naught by K ln Ca naught by Ca is equivalent to, so we can plug in all the values, right? So V naught is 10 cubic decimeter per minute, K rate constant value is 0.23, minute inverse ln Ca naught will remain as it is, and we'll put the value of Ca. Ca is equivalent to 0.01 Ca naught, right? So from here, Ca naught will be cancelled off, right, from the numerator and denominator. So after solving this part, we'll get the answer as 43.4783 cubic decimeter, and ln of 1 by 0.01 is ln of 100. Okay, after solving this, we'll get the answer of 4.6052 into this term, right? 43.4783 cubic decimeter into 4.6052, right? After solving this, we'll get the final volume V2 is equivalent to 200.226 cubic decimeter, which is equivalent to 200 liters, which means for conversion, in order to achieve the 99% conversion, okay, we required 200 liters of volume, right? In order to achieve 99% of conversion, we required how much? 200 liters of 200 liters of Plug Flow Reactor, right? 200 liter volume of Plug Flow Reactor. Okay, now see here one question which arises in mind is, for conversion of 90%, we required only 100 liters of volume, right? But if we are just increasing by 9%, right, from 90 to 99%, right, just with the increment of 9%, from 90 to 99%, we require additional extra 100 liters, right? From 100 to 200 we require extra 100 liter volume, which is a very big volume, right? For a very small conversion, 9% conversion, right? So what are the reasons behind it, right? So it is very interesting, and this part is very fundamental concept of the plug flow reactor, right? So it is very interesting to understand, okay, and it will be very interesting for you to understand the concept, okay. Why for just an increment of 9% from 90 to 99%, we required 100 extra 100 liters of volume of plug flow reactor, right? So the fundamental concepts, will delve more deeper into the understanding of all these fundamental concepts of plug flow reactor in the upcoming chapters, right? So I hope up to here you understood, right? So I request you to please make all the notes, okay? I request you to please make all the notes, okay. Now let's say some only two things remaining is one more in order to understand how the nature of flow curve came, right? So let's say the molar flow rates of A and the volume and the uh, concentration of A reactants will decrease, right, along the length and volume of the reactor, right? So let's say we'll understand like how this nature of the flow came, right, by mathematical way, okay. This is some extra part which I'm making you understand in very simplified manner, okay. So let's say if you want to understand the nature of the plot, like how we are drawing this decay in concentration with respect to the volume of the plug flow reactor, right? In order to understand that, so we can understand two terms with respect to the volume of the reactor. The concentration and molar flow rates of reactants will decrease, right, by understanding the mathematical relations, right? So let's say first of all we are understanding the concentration term, how the concentration will decrease with respect to the volume and axial direction of the plug flow reactor, right? So let's say we are writing the same equation V here. V is equal to minus V naught by K ln Ca by Ca naught. So we are using that same equation. V is equal to minus V naught by K ln Ca by Ca naught, right? We are making the subject as ln Ca by Ca naught. So for those reasons, the K, the rate constant, can be multiplied with the volume, and the nu naught, which is volumetric flow rate, can be divided in the denominator, right? We'll go to the denominator, right? So we are making the subject as ln Ca by Ca naught. So ln Ca by Ca naught is equivalent to minus K. So we are sending this minus sign to here. So minus K into V by V naught, right? And we can take the anti-log log over here, right? So Ca by Ca naught is equivalent to exponential of, we are sending we are removing this ln sign, right? So we are taking anti-log. So Ca by Ca naught is equivalent to E exponential of minus Kv by V naught, okay. We are making the subject as Ca. So Ca is equivalent to Ca naught into exponential of minus Kv by mu naught, okay. So by using this formula we can understand the nature of the plot, the concentration, the Ca here, Ca represent the exit concentration of reactants via outlet stream of the plug flow reactor. Ca naught represent the inlet concentration of initial concentration of reactants which are feeding to the plug flow reactor via inlet stream, okay. K represent the rate constant, V present the volume, and nu naught present the volumetric flow rate, right? So by understanding this equation, Ca is equal to Ca naught e raised to minus Kv by nu naught, okay. So by understanding this mathematical relation, where we can see the concentration, okay, the concentration of the concentration of reactants will decay exponentially, right? The concentration of reactants will decay exponentially, okay. The concentration of reactants will decay exponentially, okay. I hope you understood. Similar way, we can also derive a mathematical relation by using the molar flow rates, right? So let's say we'll use the same molar flow rate as Fa is equal to Ca by Ca into nu, right? So let's say Ca into V naught, because here we can replace V nu by nu naught because we are having the same constant volumetric flow rate, right? So for those reasons we can write as Fa is equivalent to Ca into nu naught, okay. We can put the value, we can plug in the value of Ca from here, right? So Fa is equivalent to Ca naught into e raised to minus Kv V by V nu naught into this nu naught. Okay, now let's say we can make these term together, Ca naught and nu naught. Okay, so Fa is equal to Ca naught into nu naught into exponential of minus Kv by nu naught, right? So here we can see C naught into nu naught represent the Ca naught into nu naught represent the initial molar flow rate Fa naught, right? Initial molar flow rate of concentration, right? Initial molar flow rate of reactants Fa naught, right? So Fa is equivalent to, okay, let's say, sorry, the Fa is equivalent to, okay, the Fa is equivalent to Ca naught. Ca naught into nu naught is Fa naught, right? Okay, so see Fa, okay, it was correct. Fa naught, it was correct because Fa naught is equivalent to Ca naught into nu naught, right? So Fa, so here Ca naught into nu naught is represented as Fa naught, right? So Fa is equivalent to Fa naught into e raised to minus Kv nu naught. I hope so. Here you can see the how the molar flow rate decreases with respect to the volume and length of the plug flow reactor in the axial direction, right? So this mathematical relation which explains the, how the molar flow rate decay exponentially with respect to the volume of the reactor, right? So we have the similar plot of molar flow rates Fa versus volume. We will have the similar plot, okay? We'll have the similar plot, okay? We'll have the similar plot. Let's say Fa versus volume. So we'll have the similar plot. Okay. So here also you can see how the molar flow rates decay exponentially with respect to the volume of the plug flow reactor. I hope you understood, right? So, in order to conclude, in today's lecture, we have solved one industrial example of the plug flow reactor, okay, where today we were aiming and analyzing and estimating how large volume of plug flow reactor is required in order to achieve the desired conversion in the product distribution, right, in the product formation, right, by using the fundamental concept of the plug flow reactor. Okay, so in the upcoming lectures, we are going to solve one more numerical based on all the reactors, right? Let's say the one numerical where we'll try to compare the plug flow reactor, continuous starting reactor, and the batch reactors, right? So for the specific reaction, for the given data, how the volume of the plug flow reactor will vary if we change, if we use, or let's say, for example, for the given data, for the given reaction, okay, how the volume of the plug flow reactor, continuous starting reactor, and the batch reactor will vary for a similar reactions, right? So you will get a very good depth insight into the numerical example, okay, and you will understand the fundamental concepts of all the reactors, right? And you will enhance your understanding for the numerical examples of chemical reaction engineering, right? So I request you to please make all the notes, right? So until then, stay focused, keep learning, and stay curious. Thank you for watching my video. JMB.